Hello, I'm going to take a quick break from the role-playing game series to have a look at programming pseudo three-dimensional planes. And this was a technique made popular by the Super Nintendo, and I'm going to use Super Mario Kart as an example, where an image is taken as the ground plane and it is rotated and scaled and translated around the camera as necessary to give the impression of a three-dimensional environment. This was known as MODE7, which for the Super Nintendo was just really implementing an affine transform in hardware. I'm not going to be using affine transforms directly because I want to play with some of the parameters and see what happens. And so this is what we're going to be developing. Of course, it's in the console. Now, to those of a certain age, this may look very familiar. This is indeed the first track, I believe, from Super Mario Kart. And for those expecting another episode of the role-playing game, you can see it's vaguely related. We're using exactly this technology for the world map. And what I think is really neat about this program is that is it. There is barely anything to it at all, so this should be a nice, short, quick video showing something interesting we might be able to use in other games and technologies. So as we usually do on this channel, let's take a quick look to just explore what it is that we're going to do, and try and understand some of the concepts and principles behind the algorithm. I'm going to create a big OLC sprite. And we know that these behave just like textures, and that we can sample from them, assuming that the top left is 0, 0, and the extremities are 1.0 and 1.0. And if you remember from the code-it-yourself first-person shooters, this makes sampling the texture scale invariant. I'm going to treat this big texture as if it were my world map, or the Mario Kart track in this case. In this map, I'm going to have a position, which represents where the camera is. And I'm going to call this position World X, and world Y. The camera will also have an angle associated with it. We're in a 2D plane here, so we don't need a three-dimensional camera. And we'll assume that the angle is what direction is the camera looking at in this plane. From this information, I'm going to create a viewing frustum, but I need a little bit more information first. Firstly, I need a field of view, and we'll call that theta. I then need two more pieces of information. I need to know what is the nearest location to the camera, and which is the furthest location from the camera. And these are going to be lines that straddle our viewing frustum. Let's draw these in. And if we were to continue drawing our camera vector, what we can see about these two lines is they are at right angles to where the camera is looking. This gives me 4 coordinates. Up here, 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 and here. And I'm going to use those coordinates to give me a region which I will be sampling to display to the user. And this is my frustum. Once we've got the frustum, we can now determine the mapping between what the player can see on the 2D plane versus what they can see on the screen. Now in the console window, we know that the y-axis goes in this direction and the x-axis goes in this direction. Well, that maps on to our frustum too. So the furthest away y location is going to be towards the top of the command prompt window, which means this becomes our y-axis and this becomes our x-axis. And we'll notice that the x-axis changes length depending on where it is in the y-axis. When we're far away, we're looking at a lot more x than we are when we're close to it. This means we can take any xy coordinate in the command prompt window, work out where it lies inside our frustum, and that becomes the sampled point that we will display on the screen. It would appear that there's quite a degree of interpolation happening, and there is. So I'm going to put some naming conventions in so we can follow the code. This point up here is going to be known as far x1 and y1. This one down here is going to be known as near x1 and y1. This one is far x2 and y2, and this one is near x2 and y2. When we extract a pixel location from the console screen, we will be normalizing it versus the screen width and screen height. So we'll be getting in a value between 0 and 1. So let's say our pixels location, x and y, is 0.5 by 0.5. That means we want to select somewhere in the middle of our frustum. But how do we know where the middle is on a shape like this? Well, we know that the y coordinate is going to be reasonably consistent. For now, those who are thinking ahead, we'll come back to that later. 0.5 will be somewhere halfway along the line between near and far. And because we know the vector between far x1 and near x1, and the vector between far x2 and near x2, we can work out where those 2 points are. And once we've got those 2 points, we create a new line. Kind of goes through the middle. So I'll just flag that in a normalized space, this is halfway along. And then of course, because we've got this line, we can do exactly the same to this new line to work out the x location, which is halfway across this new line, which we've drawn in already. It's there. And so by using this approach, we can specify any coordinates between 0 and 1 and work out where it lies within this shape. Let's just do a second example just to make sure that let's assume that instead of 0.5 we've got 0.25 by 0.75. So in this instance we would go 3/4 of the way along our line linearly, 0.75 there, and it's about there on the same. Create a new line between those 2 points, and then it says we're at 0.25 along the x-axis. Well, we know that the middle is about there, so the 0.25 must be about there. So this becomes our sampling point. Now, you may have noticed that I subtly hinted something's not quite right with this approach. But we'll come back to that when we start writing some code. And so let's get started with the code. I've already created a subclass called onelearncoder fake MODE7, and I've created a main function which creates an instance of this class constructing the console to be 320 wide by 240 high, and each character is going to be 4 by 4 pixels. Note that this is quite a high resolution, and indeed may not work on certain screens. If you're not using a 1080p screen, it's not going to fit on that desktop, so you'll have to use a smaller console size. Well, let's start by adding the very basics. I know I'm going to need a sprite that represents the ground. Later we'll show how to load the sprite, but to begin with I'm going to create it algorithmically because I want it to be a sprite of lines so we can see how does the 3D effect start to distort what the user can see. And on the whole I know that my map is going to be square and both sides are going to be 1024, so it's going to be like a 1 megapixel texture, quite a big thing for the console game engine. So in the onUserCreate function, I'm going to create it. And here we go, I've defined it as being a square sprite of size map size by map size. I want to populate this map by hand, so I'm going to create 2 nested for loops to draw lines going from one side of the map to the other in both the x and y directions. And I want it to leave a gap of 32 pixels between each line. For the opposing axis, I want to draw in every single pixel. So we skip by 1 pixel at a time. Now, even though I've used the naming conventions x and y here, I can actually draw both the horizontal and vertical lines at the same time. And that's because the map will be reflected along the XY axis. It's fine. And sprites have accessing methods, so we can actually set the contents of the sprite manually. So I'm going to set the colour at that location to be magenta, and I'm going to set the pixel type at that location to be the solid pixel. In fact, I'm going to do exactly the same for the neighbouring pixels, because this will give the line some thickness. So this will be drawing lines in the y-axis. We can simply flip the coordinates to draw lines in the x-axis. So these 2 nested for loops work to create a grid-like pattern of magenta lines in one axis and blue lines in the other. Everything else we want to worry about is in onUserUpdate. I'm going to add some variables that represent where the player is in the world, x, y and angle in radians. I will also need some variables that represent the frustum. I'm going to choose some numbers at random to begin with, so the near plane is going to be 0.01 and the far plane 0.1. I've really no idea what these mean in the scale of the map that we're creating. I'm also going to need a field of view variable, but I'm going to store instead the field of view half variable. So in this case the field of view would be pi divided by 2, but I'm automatically halving it already, so it's pi divided by 4. And the reason for this is because I'm taking the angle of the centre line from the player into the map, and I'm going to subtract half the field of view, and I'm going to add half of the field of view to give me the frustum points. So let's do this now. We want to create our first set of points, which was far, x1 and y1. Well, if we assume that the player exists at world x, we can create a unit vector using cosine and sine of the angle that the player is facing minus the field of view times the far plane. So wherever the player is in the x-axis, we're going to create a value between 0 and 1 here, and we're multiplying that value by the far plane. Again, I don't know where this exists in the space of our world. It goes without saying that to create the Y component is exactly the same, except we use cyan. For the opposing far point, we're plussing half the field of view instead of subtracting it. And for the near points, we're using the near plane value instead of the far plane value. So this gives us 4 two-dimensional points that represent the corners of our frustum within the map. When we're drawing the maps, we only want them to occupy half of the screen, not the full screen, because this assumes that our vertical vanishing point is halfway up the screen. So I'm going to work on a row by row basis within our console window, going from 0 to half the screen height. We'll need to normalise the screen height value to between 0 and 1. I'm going to call this sample depth, and it's just simply the Y value divided by the total range of the Y value in this case. Knowing how far into the frustum we need to be, we can create 2 points that represent the scan line going across the frustum. So on the left hand side, the x1 side, I get the direction vector of the line of the side of the frustum. I multiply it by my normalized value to create a sampling point, and I offset it by the near plane. And I get an end point for the scan line by doing exactly the same thing. Now we know where the scan line begins and ends in our frustum, we can use the x component of the screen coordinate to work out where along that line we should sample the pixel and colour. So in exactly the same way, I'm going to create a normalized point between 0 and 1, sample width, and I'm going to find the sample location by interpolating along that line. Once I have my sample coordinates, I can go and extract them from the OLC sprite using the sample glyph and sample colour functions. Now, these functions will operate on a nearest neighbour principle, which means we don't really care about the spatial scale in this instance. The sampling algorithm will do what it should do, and will never give us any holes or blanks. Once we know which symbol to draw and which colour it is, we should draw it. But I'm going to draw offset by half the screen height in the y-axis, so this gives us a ground plane along the bottom of the screen. Let's take a look. Well, something's going on. From that static image, I can't really work out what's happening. I need to add some user controls to move the player location around the map. And I will add these outside of our rendering loop. We've seen this many times before. I'm just going to see if the left arrow key is held down, and if it is, I'm going to decrement the angle. If the right arrow key is held down, I'm going to increment the angle. If the up arrow key is held down, then I want to increment the x and y coordinate along the unit vector created by the angle. And I'm going to increment at this particular speed. It's quite slow. But at the moment, slow is relative because I've no idea what the scale of our world is. This will take a little bit of fiddling about and getting a feel for it. And I can do the same for reverse, except this time I'll put a minus sign in front of the cosine sign. Let's take a look. Well, I'm turning in the world, and it's looking pretty funky. What I noticed though is that the world seems to end quite quickly. Let's try moving backwards. Well, that was strange. And moving forwards, well, it's just outright psychedelic. It's pretty, but useless. The problem here is I've just taken a guess at what our near and far plane should be, and our field of view. So I'm going to make these controllable too. Similar code, I'm just going to check for certain key presses and alter the parameter by incrementing it or decrementing it. Let's see how this works. So, without turning anything, Q and A change the plane's near parameter. Well, that seems to stretch things out. W and S change the plane's far parameter. Well, we can see there is change, and I guess it kind of makes some sense. The field of view is changed by Z and X. And that's definitely affecting things in the X-axis. Let's rotate the player into the scene a little bit, and we'll widen the field of view. And we'll try changing the far plane a little bit. Change the near plane a little bit. Well, that kind of looks like we're just looking top down. So rotation and sampling and things are working, but something's not quite right. If I orientate the camera so we get vertical and horizontal lines somewhere in our scene, we can see that they behave kind of appropriately, but it looks like our scene has its perspective firstly in the wrong direction and upside down. So as the player is moving forward here between the two magenta lines, the blue lines are behaving somewhat sensibly. And if I rotate 90 degrees, so that we're now travelling along the blue lines, the magenta lines behave somewhat sensibly. So it is kind of working, but it's clear that our perspective projection is, well, rubbish. And surprise, surprise, this is our problem. We've made a rather naive assumption that our interpolation along the frustum central axis away from the camera is linear, and it isn't. Perspective assumes that we've got three components to an image, x, y and z, where z is equal to the depth. And we intuitively know that things that are further away move less and have less significance. And so if we were to look at the relationship between depth and x and y, what we might be able to assume is that some new position x is equal to some position x divided by depth. And the same goes for the y-axis. And this implies that as z approaches infinity, any changes to x become minuscule, whereas if z approached 0, the changes become very large indeed. And in many ways, I suppose this is why the stars in the night sky don't appear to move as you move your head around, yet the trees and lampposts in front of them do. But what's interesting here is that we're seeing that depth is certainly a 1 over depth relationship to x and y. I thought it might be useful to quickly explore why this might be the case. I want you to imagine for a minute that the camera is the man's head, and the man is looking forwards into the world. What can the man actually see if we broke the world up into scan lines? So here I've projected two rays from the player's eye into the distance. And if we were to attribute how much of this distance scan line can be seen by the player, we might want to estimate it by drawing a little arrow between the two. We can see it's quite small. Let's draw in some more lines. And now if we look at the proportion of what can be seen for each scan line, we might be able to identify a bit of a trend. And I'll very carefully try and draw this line in, joining all of the points of these up. Look at that, I'm getting somewhat better with the old drawing tablet. We can see very clearly that we have indeed got a y equals 1 over x relationship here. What this means in real terms is that we're not looking in the right place for our frustum. Instead of this line being broken up linearly, we want to look at it in a slightly different relationship, where those lines close to the player are close together, but as we get further away from the player, they get further apart. And we can also see here that this equation is not quite correct. We're starting with the scan line that's furthest away, yet our sample depth variable assumes the nearest line. So let's see what happens if we flip this round. Well, it still looks a bit rubbish, but we could assume that now at least things are moving in the right location. As I move along now, the perspective is corrected towards the player, and the vanishing point lines disappear into the distance. Let me just play with the planes a little bit. So there we have it. I can rotate 90 degrees, but there's still a great degree of curvature, and that's because we're still operating linearly. And I can do this in one hit. We know that the first line we're calculating is the furthest away, but that requires our scan line to be the largest in width and yet the most minimum in detail. What I'm going to do is not flip this round. Instead of multiplying, I'm going to divide. So starting with the furthest away scan line, our sample depth is effectively 0. Yes, there's a little bit of a divide by 0 here. But in this case, let's assume that's infinity. It means as far away as we can possibly see, we can see everything. But as we get closer towards the player, we start to approach 1, which means the scan line becomes very small. Now let's take a look. And what a difference that has made already. I can rotate the player, and I'll move forwards into the map. And we can see, despite a few sampling issues, we can walk up to the boundaries of the map. Let's just take a minute whilst it's working well to play with our parameters. So the field of view, well, widens and narrows the field of view, as you might expect. You'll have seen this effect in quite a lot of first-person shooter games. If we alter the near plane, we can start to imply a degree of curvature to the map. Let's try and straighten that back up again. There we go. And if we alter the far plane, it gives us the impression that the camera has risen from the ground. And of course, that's because that's the only way that equation can be solved. If we're saying that the far plane has to be wider, the player needs to be higher up and further away. So this leads to some promising things. We could have a jumping mechanic. But one thing I have noticed is the world ends, and this might be undesirable for emulating things like globes in role-playing games. See where I'm going? So because our sample positions are calculated in world space, but our map is a finite texture between 0 and 1, I'm going to take the floating point modulus of our sample coordinates. So this should implement a wraparound functionality. And so we've not got a wraparound. We're currently at 0, 0, so we don't have anything in the negative axis, but we can see the map goes on indefinitely away from 0, 0. So what we might want to do is place the player somewhere in the middle of the world first, so they're nowhere near the negative edges of this map. I'm going to pick a number, 1000. And that's nice, so we can see that the player is now stood within the middle of the world. I think it's time to say goodbye now to our hand-generated map and use a preloaded texture. So I'll comment that out and load the texture directly. Now I went online to have a look at Mario Kart maps and found a fantastic website which had them as PNG files. And as some of you may know now from quite a few videos, the fantastic King from the Discord server has been creating lots of algorithms to turn PNG files into console game engine format sprites. And so I converted the PNG into a sprite ready to use in the game engine. So let's have a look. And we can see, well, we've certainly got a map. It looks a bit distorted and parallel lines aren't quite right, but that's why we've got adjustable parameters. So firstly, it looks like I'm floating in the air. So I'm going to adjust the far viewpoint down a little bit so it brings me closer to the ground. I'm going to bring in the near parameter to try and take out some of the curvature. So I can put in lots of curvature. It just makes it look like we're always going downhill. We want to try and iron that out a little bit until it looks about right. There we go, that's not too bad. The field of view seems reasonable anyway. We can make it wider and we can make it narrower. I think in racing games you can change the field of view to give you different perceptions of speed. So as I make the field of view wider, I'll just try and zoom along in a particular direction. So the field of view is getting very wide, but if I bring it in and come a bit narrower, yes, I think it starts to look like we're speeding up. Maybe, I don't know. It needs some playing with. One thing I am curious to see is how does the Mario Kart map look if we don't do this perspective correction. Maybe it'll be clearer to see what's going on without the blue and magenta lines. So we can see it's upside down again. Maybe if I just zoom out a bit. So now I'm altering the far plane, and we're getting these sort of inception-like rolling. And that's simply because it is upside down for a start, but we're attributing perspective in the wrong place. We're basically seeing the furthest away parts of the world in the most detail. And it's very disorienting. Let's put that back. One of the benefits of having calculated all of this maths for one texture is we can use exactly the same coordinates to sample a second texture for the sky. So I'm going to add another sprite, sprite sky in this instance. I'm going to load that. And here we're sampling the ground texture and drawing the sky, I'm going to just use exactly the same coordinates and variables again to sample the sky texture. We don't need to calculate it because it's in the same place relative to the ground. But this time, instead of drawing offset with the screen height, I'm assuming I'm drawing from 0 to the middle of the screen. But I want to draw it upside down in this instance, or else it'll look very strange. Let's take a look. Well, there's our screen. For some reason it's divided into quads. That one looks to be like it's a close to 0 sampling error, somewhere to do with the sampling of the OLC sprite. But now we can see the sky behaves in exactly the same way as the ground. This is very good. So if we increase the far plane, it works for both of them. So it makes the environment appear a lot more vast. Make it very big. It takes a slight hit in frame rate now, but we can make the environment appear very big or very claustrophobic. Might be interesting to do some sort of first-person shooter with this. If we alter the near plane, well, we'll start to get some weird curvature effects again. I'm going to have loads of fun playing with these parameters. What I have noticed is a big ugly black line in the middle of the screen at the horizon. And that's because of this infinity value that we talked about before. We can see it is here in the ground map, and it's also here in the sky map. Well, I tell you what, in this instance I'm going to cheat. I'm just going to draw a cyan line at that location. Take a look, and there we go. And the nice thing is, because this is just a 2D map, we could store all sorts of additional information. So for example, these squares, they could be solid, and we wouldn't be able to move the player past them. We might be able to interpret a secondary texture that contains track or not track information to give us different levels of grip. This approach gives us quite a lot of possibilities for interesting games in the future. Anyway, I hope this video has been of some use to you. If you've enjoyed it, please give me a big thumbs up. Thanks to King on the Discord server for creating his PNG to sprite converter. Have a think about subscribing, and I'll see you next time. Take care.